Alright, we're going to be looking at Concept Y. This is just for the honors students. We're going to be covering the Universal Gas Law. So basically, the Universal Gas Law allows us to look at the behavior of a gas in regarding the number of particles as well as the other environmental factors such as pressure, temperature, and volume. Now, we know that the number of particles is a direct relationship to pressure as well as a direct relationship to volume. If we're going to hold all other constants or all other variables constant, if I increase the number of particles, it's going to increase the pressure. If I increase the number of particles, it also would have to increase the volume to keep everything else constant. The only difference here is that the number of particles is an indirect relationship with temperature. If the number of particles go up in order to keep pressure and volume constant, the temperature actually has to decrease in that case. So keeping this in mind then, we have that PV over T and how it relates to our number of molecules. And this PV over T should look familiar from our gas calculations that we did in a previous concept. Now we're going to be looking at what we call the ideal gas law, specifically involving a new variable here where R is going to be a constant in all of our calculations. So this is the important equation. Now this isn't on the back of your reference table because it isn't part of our Regents curriculum, but this will come up on your test. N is our number of particles, and R is that universal gas constant, which is 0.0821 with this massive unit that you need to know and be able to fill in. So liters times ATM over moles times kelvins. And then a couple things to keep in mind to note in your packet. Volume has to be in liters. Pressure must be in ATMs. N has to be in moles. And then temperature must be in Kelvin. So we're going to go through a couple of practice problems so you can see how this works. So how many moles of an ideal gas will take up 0.1 liters at a pressure of 2.5 atmospheres and 298 Kelvin? Well, we start with our universal gas law, so PV is equal to nRT. We're going to fill in all of our given values. So we have our pressure in ATM already, 2.5. Our volume is 0.1 liters. And our number of moles is going to be our unknown. R is going to be the same for every single one of these calculations, our universal or gas constant, and then temperature is 298, which is already in kelvins. So going ahead and multiplying and dividing, you should get on your calculator 0.01 moles of this ideal gas. It's as simple as that. Let's look at a couple of things that add some other factors in. So what is the pressure in kilopascals, not ATMs, on a 600 milliliter sample of gas at room temperature if it holds 0.2 moles of gas? So a couple of things. We are asking for the final answer to be in kilopascals. We also have milliliters, which we need to keep in mind. We're going to have to change. So using our formula, PV is equal to nRT. We're going to go ahead. You can see that we've taken 600 milliliters and I've changed it into liters, so 0.6. I basically divided that by 1,000, or you could set up a conversion factor. We have our number of moles, which is N, our universal gas constant R, and then our temperature, which was already in 298, which at room temperature, remember, is 25 degrees Celsius. So make a note of that. We've talked about that in a previous unit, room temperature. So 25 plus our 273 because it's 298. All right, and then again, multiplying and dividing, you would get a pressure initially at 8.16 atm. Now remember, I wanted it in kilopascals. And if you go back to concept A, we talked about the equalities that exist between the various units of pressure. So using that, we can set this up as 8.16 atm. Our conversion factor, if I started with atm or putting 1 atm in the bottom, that's equal to 101.3 kilopascals. Multiplying across the top, dividing by the bottom, you get 827 kilopascals. That will be the pressure of this sample of gas, and specifically an ideal gas. All right, calculate the amount of space 1 moles of gas will occupy at STP. So one thing to keep in mind, and I specifically underlined this for you, remember STP to you now has to represent numerical values. So we have PV is equal to nRT. We're going to go ahead and plug in our information. 1 atm is the standard pressure. Our volumes are unknown, our amount of space is what we're looking for. We have 1 moles, we have our universal gas constant, and then the standard temperature in Kelvin is 273. So going back and using table A to help find standard temperature and pressure. And then solving for volume, you get 22.4 liters, which this should make sense that 1 mole of a gas at STP is going to occupy the 22.4 liters, which we talked about before. All right, this one has a couple of interesting things going on. We're actually given the amount of carbon dioxide in grams, and we're also given the pressure in torrs. or torricelli. So we want to now calculate again the volume, but we're going to do a couple things first. If we're given grams, we need to convert 2 moles, so I'm going to use the GFM of CO2, that's the 44 grams. So if I start with my given as my 8 grams, then grams, or the GFM, has to go in the bottom of the conversion factor, and that's equal to 1 mole. I'm multiplying across the top, dividing by the bottom, so 8 divided by 44 gives us 0.1818 moles. And then also we have to go from torr to ATM. So again, the equality between this is that 1 ATM is equal to 760 torr. So if we start with torr, we got to put the torr part on the bottom of the conversion factor. So 500 times 1 divided by 760 gives you 0.6579 ATM. Now we can go ahead and actually plug this into our universal gas law. So PV is equal to nRT. We're going to plug in our pressure, which was given in the converted to from torr to ATM. We have our moles now from grams to moles, our universal gas constant, and then our temperature. Remember, room temperature is 25 degrees Celsius, so 25 plus 273 gives me 298 Kelvin. And then going ahead and multiplying, dividing, I get my volume at 6.76 liters. So most of you guys know how to plug this into the given formula. You just have to be careful for checking for units, especially. Your unit here for the universal gas constant gives you a hint of what all the units should be. So it's important to take note of that because that will help you out later on. Well, that's actually it. So we will practice this calculation more tomorrow, and you are all set. So go ahead and write your summary or go ahead and take the quick quiz.